Last video, we looked at a different classification of compounds called molecular compounds, and we focused in on how the chemical formulas and names can be derived for these compounds simply by using a prefix methodology of indicating how many of each type of atom are in the compound. In this video, we're going to dive a little deeper into the actual structure of these molecular compounds and what they look like at a bit of an atomic level. We will use Lewis structures to help us with this. So a little bit about covalent bonds. Covalent bonds are very, very strong bonds. They take a lot of energy to break. They form when two nonmetal atoms share electrons. And these shared electrons count towards obeying the octet rule for each atom, which was still a criteria used for ionic compounds as well. It's a slightly different methodology. And so we're going to begin our discussion by looking at two very, very simple molecules that involve covalent bonding. Let's begin with something called H2. This is actually elemental hydrogen. Hydrogen, when we draw the Lewis dot diagram for it, has one dot located there at the 12 o'clock position. And because this chemical compound says that there are two H's, I'm going to take a moment to clone this so that it has a partner right there. And what we need to remember is that these atoms are in three-dimensional space. And so even though we're putting them on a two-dimensional surface, we have the ability to take them and rotate them any way we like. And what I'm going to do here is I'm going to take these two H's and rotate them, if you will, towards each other so that their single electrons are facing each other. And when those single electrons come towards each other, they form what's called a covalent bond. And what we do to indicate on paper that a covalent bond exists between them is we allow these single electrons, if you will, to hold hands, or we can connect them with a solid line. Now I realize that the H's are written sideways here, so I'll take a moment just to put them right side up. Now the great thing about this covalent bond is that this new straight line joining the two H's contains those two electrons, and those two electrons can count towards filling the outer shell of this H, but they can also count towards filling the outer shell of this H as well. And we know that hydrogen only has electrons in the first energy level, and therefore by sharing these electrons and counting them both ways between those shared atoms, this hydrogen now has a full outer shell, and so does this one. And so this is a great way for them to come together. Let's take a look at another example. Let's take a look at F2. And because it says F2, I'm going to take a moment to clone this one as well. And so when I'm looking at drawing the Lewis structure of this molecule F2, I want to identify first off, where are there some single electrons or ones that are not already partnered up? You can see here there are some that are partnered up, and here there are some that are partnered up. But let's identify where those singles are. Now, if we allow those single electrons to be rotated and come towards each other, and I'm just going to do this by turning this one upside down here for a moment, and we'll also pick it up and bring it towards this one, we can see that those new single electrons can come and form a shared pair of electrons. And so instead of having them as just single electrons pointing towards each other, let's show the fact that they're shared between those two fluorines by connecting them with a straight line. And this straight line indicates a covalent bond between them. If we do an octet check now between these two fluorines, we can see that fluorine number 1 here has 1, 2, 3 lone pairs for a total of 6 electrons, but then this covalent bond that is between them consists of 2 electrons, one from each fluorine, and we can count that shared pair in each direction for each fluorine. So fluorine number 1 has an additional 2 electrons for a total of 8, and therefore its octet is full. And because of symmetry, you can appreciate that in fluorine number 2, a similar scenario exists. So in the case of H2 and F2, a single covalent bond is used to bring the atoms together to fulfill their octets. There's no loss of electrons and there's no gaining, there's a sharing. Let's look at some more examples. In this case, we can look at O2. O2 has 2 oxygen atoms, so I'm going to take this one here and I'm going to clone it again. And here we go. And you'll notice this time when you do the Lewis dot diagram of oxygen that there are 6 valence electrons around it. We know that because it's in group 6 of the periodic table. And when we place them around oxygen using the 12-3-6-9 rule, in other words, at the top, to the side, bottom side, and we fill them singly then doubly, we end up with a structure that looks like this. Now, let's identify where those single electrons are in oxygen. And we can see that in the case of each of them, there's one along the bottom and there's one to the left. Let's orientate them so that they are facing each other. So I'm going to pick up this oxygen and we're going to rotate it this way so that those 2 single electrons are facing that oxygen. And we'll do the same thing over here. And then we will bring them closer to each other. There we go. Now, in doing so, oh, I made that one a little larger. Let's bring that back down. There we go. Okay. In doing so now, these identified single electrons can create a covalent bond between each other. And they can share towards these oxygen. Let's do an octet check to see what happens here. This first oxygen has 2 lone pairs of electrons for a total of 4 electrons from here and here. Then this shared pair, of course, counts in both directions towards each oxygen. So in oxygen number 1 here, we have 2 electrons from that covalent bond, and we have another 2 from the covalent bond above it, for a grand total of 8 electrons, or obeying the octet rule. And you can appreciate from symmetry of this molecule that the second oxygen would also have a full octet. So in this case, where there are 2 shared pairs of electrons, we call this a double bond, or a double covalent bond, because there are 2 pairs instead of 1. Let's look at our last example here for nitrogen. For N2, we're going to need another nitrogen. And when we're looking at drawing the Lewis structure of this molecule, our first question is where are all the singles? And the single electrons are located at the 3, 6, and 9 positions of the clock around that N symbol. What I'm going to do then is I'm going to rotate this so that those singles can be orientated towards each other. And we'll bring this one closer as well. And you can see in this case that because there are 3 singles, there are 3 bonding opportunities for some other atom. In this case, the other atom is nitrogen. So we can connect here, and here, and here. I'm going just to redraw that molecule underneath so that you get a sense of what it looks like with the ends being in the proper orientation alphabetically. So in this case, the nitrogen on the left and the right are symmetrical, but we can see that regardless of which nitrogen we speak of, there are 2 electrons from the lone pair that exists out here, and from the bonding pairs here, each one of those lines represents 2 electrons, and 2 times 3 means there are 6 electrons that are involved in bonding for a grand total of 8 electrons, counting towards each nitrogen. And again, that means that we can obey the octet rule. So the examples that we've looked at just now, H2, F2, O2, and N2, are known as diatomic molecules. Diatomic because di means 2, and atomic, of course, means atom. It's also implied with those diatomics in this particular scenario that we're talking about pairings where the 2 atoms are identical, 2 H's, 2 F's, 2 O's, or 2 N's. Now what's really interesting is there are actually 8 elements on the periodic table that exist in their natural states as diatomic molecules. And I want to give you a couple of ways to try and remember that. One student I've had before has come up with sort of a little acronym here called Hofbrinkel. And Hofbrinkel helps you remember that the 8 elements on the periodic table that do exist as these Siamese twins pairs, if you will, are hydrogen, oxygen, fluorine, bromine, iodine, nitrogen, and chlorine. And that helps to remember. I have another rule that I came up with, sort of my acronym, called the Rule of 7. And you're more than welcome to use it as well. So for the Rule of 7, if you start at element number 7 on the periodic table, which is nitrogen, and you go across here to oxygen and fluorine, which are elements 8 and 9 respectively, and you head downward, So we have chlorine, bromine, and iodine. We kind of stop there. Okay. You'll notice that this makes sort of like a shape of a number 7, and it starts at element number 7. Now, the only problem with my acronym is that there are only 6 of the 7 elements shown in this number 7, and so there is one more. The other one is hydrogen, and it's kind of, if you like to think of it, you can think of it up here if you want, but of course it's element number 1 over here on the periodic table. So 7 elements that exist as diatomics in their natural states. At this time, I'd like to point out that there are a couple other elements that are a little bit of exceptions to the rule as well. And they are actually located right underneath this number 7 on the periodic table. Phosphorus here actually exists in its natural state as P4, or little bundles of 4 phosphoruses together, sharing covalent bonds. And sulfur, which is here, in its natural state, actually exists as S8. Okay, so all of these, again, ones that are part of the group of 7, exist as diatomics of themselves, and phosphorus has 4, and sulfur exists in bundles of 8. Other than that, all the other elements exist as single atoms of themselves. They are not actually connected to each other. They can be in groups, but they're not bonded to one another. So what I'd like to do now is up the ante a little bit. Let's explore some covalent bonding for molecules other than diatomics, or things that are a little bit bigger. And I'm going to show you some strategies you can use to come up with the Lewis structure of a small covalent molecule. First of all, we're going to look at water. And water, when we break it down, consists of an H and another H and an oxygen. An oxygen, being in group 6, has 6 valence electrons. And so when we look at water, we can see that the total number of electrons that we have to play with in this puzzle, if you will, is equal to 1 plus 1 plus 6. 1 for each of the hydrogens and 6 for the oxygen, or a grand total of 8. Now, if we take that number 8 and we divide it up into electron pairs, in other words, it's like taking 8 shoes and putting them to pairs, we would discover that corresponds to 4 pairs. Now, out of those 4 pairs, some of them will be bonding pairs, meaning they're covalent bonds, and some of them will be lone pairs. There's a way of taking this number 4 and divvying it up between bonding pairs and lone pairs for molecules that obey the octet rule. So what we can do is we can figure out, of those 4, how many of them are actually bonding pairs. And this is kind of a wordy equation, if you will, and I'll show you how it works after. The total number of bonds is equal to the total number of valence electrons if every atom was full, minus the actual number of valence electrons in total that you have to work with. And when you take that and you divide it by 2, you will get bonding pairs. So let me show you how that works. For number of bonds, I'm going to go down here for water. If hydrogen had a full shell, it would have 2 electrons, because it only can have valence electrons in the first energy level, and 2 is the max. Another hydrogen would also have the same scenario, but oxygen has the ability to have an outer shell when full that has 8 electrons. So we take that and we subtract the number that we actually have to work with in our Lewis dot diagram, which we calculated right here as being 8, and we divide that by 2. That will tell us how many bonds are in this structure. So a little bit of simple math. We have 12 minus 8 divided by 2 means that there are 4 divided by 2, or there are 2 bonds in this particular Lewis structure. So of those 4, 2 will be bonding, and then 4 minus 2 means that the remaining 2 must be lone pairs. And sometimes that's a really useful thing for us to know. So let's take a look at water. When we go to draw the Lewis structure of it, we're going to choose the atom that has the most single electrons in it. So in this case, that would be oxygen. And we'll put it in the center. That takes care of this one. We're going to add hydrogens where we can to help make some partnerships or some covalent bonds. And we see here and here. And lo and behold, this structure matches the notion that we have 2 bonding pairs and 2 lone pairs.